All right, welcome to the technology track. I hope you have enjoyed the conference thus far. We're here at the second day, and I'm super excited for our next lineup of speakers. This block is going to focus on fusion-based additive manufacturing with metals. Our first talk is by Samantha Webster. Samantha Webster is a PhD candidate in the Advanced Manufacturing Processes Laboratory, led by Professor Jian Chao at the Northwestern University. Her research is in metal additive manufacturing technologies with a focus on fundamental interactions and formation of defects in directed energy deposition. With knowledge of, she's recently begun research in hybrid metal AM techniques to address defects and challenges in metal AM processes. She's received the National Science Foundation Graduate Research Fellowship for her work, and she was recently named one of Society Manufacturing Engineers 30 Under 30. Congratulations. With the intent to help people through science, her plan is to continue developing fundamental knowledge in metal additive manufacturing technologies to support fabrication of unique functional designs. And Samantha, I'm so happy to have you here, and I'll leave the floor to you.
Awesome. Thank you so much. Great to be here. I'm going to go ahead and screen and get started. Okay, hello everyone. Again, I'm Samantha Webster. I'm from the Theoretical and Applied Mechanics program at Northwestern University. I am in Professor Jian Chao's lab in the Advanced Manufacturing Processes Laboratory. And obviously my research, again, is in metal AM. And today I'm going to be talking about physical mechanisms in hybrid additive manufacturing. I'm actually going to introduce a process design framework that I've developed. So first, backing up quite a bit, I know most people here should be familiar with additive manufacturing, but just in case, additive manufacturing is sort of like putting together a cake. Cakes have layers. You have layers of cake that you stack on top of each other. This makes a 3D geometry, and you finish the cake by covering it in frosting, maybe putting decorations on it, etc. So this is just an example of a simple cake. But what if we wanted to change the geometry of our cake? What if we wanted a multi-tier wedding cake with a lot of fancy different decorations? This would require a different set of tools. It would require professional baking tools and a lot of other skill sets. Same thing with what if we wanted to make our cake out of different material? What if we wanted a sushi cake? This requires a different process, a different way of building things. And essentially, in order to go from a less complex geometry to a more complex but more desirable material, we need to develop manufacturing tools that can accomplish this. So obviously the family of technologies that has recently made this happen is additive manufacturing. I've shown here the 7 different types of families based on a standard, and I just want to say that today I will be focusing specifically on powder bed processes and directed energy deposition, or DED processes. So a little bit more of example about these processes. I'll specifically be speaking about laser metal additive manufacturing. So I've shown an example of powder blown DED on the left. This is actually the additive rapid prototyping instrument that we have in our lab. It's a custom built DED machine, and what I mainly do research on. We also have LaserTech 12, a laser powder bed fusion machine on our campus. So laser metal additive has very unique structures in as-built materials. Looking at the process structure property relationships of these materials, we have very fast solidification and cooling rates. This obviously controls the structure of our material, the grain shape and size. And a lot of the time, the fast rates, and the thermal gradient throughout the material actually leads to very elongated and columnar grains, as you can see on the right. So this could be desirable in some cases, but it's important to understand the structure of your material and how you can change it. So anisotropy in AM has been a unique issue that people have been researching. There's also very unique structures in the shape of pores. So pores are one of the most common things that are removed or post-processed in metal AM. This costs a lot of time and money, not to mention critical material failure in load-bearing situations. So the vast majority of pore characterization is just through X-ray CT, and I've shown an example here of pores that are in a single layer DED part. So why do we care about pores so much? Is specifically the pores have to be hipped or the parts have to be inspected in order for them to be used. It would be better if the pores were mitigated or controlled to an extent. So they also affect the fatigue life of the part. If you have pores, subsurface pores, it will actually greatly reduce the fatigue life. So since I've again mainly worked with defect formations in DED, but I was looking into ways of how we can mitigate this. How can we either control or change the shape of pores and how many there are to target better performing materials. So I looked into hybrid additive manufacturing, but what is actually the definition of a hybrid AM process? We already have a large family of additive manufacturing processes. And when I was looking through the literature, there were very, very broad definitions of hybrid processes. It's normally just two processes that are added together. And so I've rigorously defined a metal AM definition in which it is an in situ or series combination of an additive manufacturing process and secondary energy source in which physical mechanisms are fundamentally altered or controlled to affect the resulting properties of a material and or a part. I know that's a little long-winded, but it is very specific. We take an AM process and an energy source, and then using that energy source, we can essentially control a physical mechanism within the material to so an example of this is using wire arc additive manufacturing with a second. Here we see the WAAM process with a laser beam that is included within the melt pool. And
An oscillating laser beam was used.
And the changes in the melt pool flow pattern actually allowed the release of pores from the melt pool up to the surface. So this is just one example. I'll be going over a couple of different ones later in the presentation. But first, looking at a little bit of background on hybrid AM in general, it is clearly starting to catch on. This is the list of published papers for the last 30 odd years, where we've seen a exponential uptick within the last 20 years of hybrid metal AM processes. But with so much information on these processes, where can we go from here? How can we categorize them and think about the future of these processes? And that's why I've I've developed a process design framework. So essentially over 100 papers were analyzed in the studies and relationships that I'm going to show you. So 100 papers were used to gather data and relationships on hybrid metal AM processes. And it was very clear from all of this research, there was a need to create a framework to synthesize hybrid metal AM processes and drive further manufacturing innovation. And without further ado, this is the framework. It relates the physical functional property all the way back to the hybrid AM process. So we go from the physical or functional property of interest. It is changed through a mechanism the mechanism is controlled through an energy source, and that energy source and AM combination defines the hybrid AM process. So data from all of the papers was collected in each of these categories and ultimately synthesized. But first, I'm going to talk about first the 5 sort of unifying mechanisms that I found throughout all of these papers. And so across all of this research, the main mechanisms that were used to control the properties of a material were melt pool dynamics, microstructure development, the stress state, surface evolution, and thermal gradient. Here you can see the relative amount of research being put into each of these categories. But overall, the most common things to control was the surface evolution, in which the hybrid processes essentially affect the surface properties. So trying to mitigate surface roughness of the materials, either through machining or laser remelting. Residual stresses are also a well-known thing in AM materials. And so the stress state was often controlled through a secondary energy source. Melt pool dynamics are mainly affected in deposition rate, or the melt pool flow pattern, and velocities in the melt pool. The thermal gradients actually either looked at or controlled temperature gradients within the melt pool, so very local temperature gradient, or even looking at the global thermal gradient. Microstructure development is obviously influenced by both melt pool dynamics and thermal gradients, but there are specific energy sources that were used for only looking at the microstructure. So next, looking at the types of energy sources that have been used. We have mechanical, magnetic, electric, acoustic, thermal, and plasma. So it's very evident in this donut chart that mechanical and thermal energies were heavily utilized across the board. They're very easy to implement, and it was very obvious energy sources to use with AM materials. Things that were researched less were obviously magnetic, electric, and acoustic. Magnetic fields can actually be used to change the melt pool flow and velocity. And acoustic energies were commonly used for workpiece vibration in order to release pores, as I had mentioned before. So again, all of this research and all of these papers sort of looked at this as a top-down process, where they went from the hybrid AM process, what energy source did they utilize, what mechanism came from that, and then what were the resulting physical and functional properties. However, we want to drive innovation through this framework. So we flip this around and start with the properties of interest, determine what mechanism we want to use, how we can control that mechanism through an energy source, and ultimately define our hybrid AM process. So looking at this framework a little bit more in depth, I've categorized the current research within each step into major identifiable groups. I also connected major relationships between each of these blocks. That you can find that in the paper itself. There are too many relationships to go over at this time, but looking at the major blocks in physical and functional properties, we have mechanical properties, the microstructure, and also the surface finish of the material. Again, we have listed out the 5 dominant mechanisms that were found in the metal hybrid AM processes. And here I've actually shown that the melt pool dynamics and thermal gradients will influence microstructure development as well. Again, the energy sources that have been utilized. And finally, these are a lot of examples of hybrid AM processes that have been implemented. The first category is laser, which includes secondary lasers, primary laser remelting, laser shock peening, etc. Second is magnetic and electric fields. These have been static or oscillating fields have been applied. Machining is pretty obvious, but between milling or other types of machining to reduce surface roughness. Mechanical compression, which includes rolling, ultrasonic impact peening, or friction stir processing. Mechanical disturbance, which was the acoustic energy that I was talking about before with workpiece vibration. And finally, heating and cooling, where cooling nozzles or induction heating were used to influence the material. So revisiting the 5 dominant mechanisms, I'm going to go into detail on 2 of them. The first is going to be melt pool dynamics, where we're going to look at how specific processes can fit into this framework and how this framework can be utilized. So again, melt pool dynamics specifically looks at how to control the melt pool size, the deposition rate, or the melt pool flow pattern and velocity. So as a first example, we have our property of interest, which is porosity. We can influence it through melt pool dynamics with a magnetic field. And in this case, a static magnetic field was applied. So this was a vertical magnetic field in an SLM process. And essentially, magnetohydrodynamic damping causes the melt pool to break. So normally we have very strong Marangoni convection in the melt pool in metal AM processes. Magnetohydrodynamic damping can actually reduce that velocity. So in this case, the melt pool velocity was reduced by about 84%. And it allowed bubbles to be released rather than trapped in the Marangoni vortex. The second example is looking at geometric accuracy that was influenced through melt pool dynamics using a thermal energy source in the form of a secondary laser. So in this process was wire arc additive manufacturing with a trailing laser beam. And essentially, this not only increased the melt pool volume, it also led to a 35% decrease in standard deviation of the melt profiles. So since the melt pool was larger, it was able to it was not as essentially wavy behind the process. Going back, and now I'll be speaking about microstructure development, where we can look at effects on grain size, the grain orientation and texture, as well as phase and element composition. So looking at grain size and grain texture, using a thermal energy source through primary laser remelting, where laser remelting was performed on each layer. This led to grain refinement and homogenization. You can see in the EBSD maps that we have very prevalent columnar grains at the start, and with more remelting layers, we actually switched to equiaxed grains. There is a caveat in this particular material. L12 precipitates were available in order to assist the transition from columnar to equiaxed grains, but it is still a hybrid process, and that is still, the capability still fits within this framework. So these have been a few examples of the research that has been done before. Now looking out at the future of hybrid processes, first looking at the promising properties that have come from this research. In general, the maximum mechanical property values achieved through hybrid process
as opposed to only AM
process. So
the red stars are hybrids. You can see across the board that we can get better material properties
with the exception of alloy 718 in this case, and that's because of the lack of heat treatment afterwards in this particular case. We can also see between UTS and grain size, smaller grains were achieved overall for the particular materials presented here. These were the 3 materials that were mainly researched. And with the exception of titanium, which has a habit of forming very long beta grains in a material. Yeah, so overall, there's a very promising outlook for properties that can be achieved with hybrid versus AM only processes. So going back to the framework, I've established major connections between all of these categories, but were the mechanisms and energy sources all researched the same amount? Were they given the same level of attention? They definitely weren't. So a lot of research can still be done in the thermal gradients mechanisms, as well as stress state and melt pool dynamics. Another thing that I noticed in going through this research is that the number of, or the types of properties that are reported in each study are not uniform. So a lot of people either focus on microstructure or they focus on mechanical properties. It's very important going forward to look at both of those and how mechanisms and hybrid processes influence both of them together. Additionally, looking at gaps in energy sources, obviously mechanical and thermal energies were widely utilized. It's very important that we look at other energy sources such as magnetic, plasma, or electric energies in the processes to So a couple of other inconsistencies of this research is one, it would be very important to develop experimental evidence of the Marangoni versus the magneto-hydrodynamic damping. Experimental evidence is needed in that category. There was also a discrepancy in the effect of applying magnetic or mechanical energy to influence the phase and composition changes in materials. There are also some opposing results of using secondary lasers, and it would be very important to use numerical prediction for laser shock peening and intralayer rolling. I also didn't talk very much about process chains, but this framework does also use is also applicable to process chains where you have an AM material and then machine it afterwards, or do some other post-processing step afterwards. Supply chain and product innovation is very important, as well as incorporating general manufacturing chains. Finally, a look at future research avenues in hybrid AM. First is model development and experimental validation. There is a huge need for in situ monitoring and measurements, specifically, as I said before, magnetic and acoustic manipulation of the melt pool would be very interesting, as well as measuring in situ pore content. Hybrid AM in general, I think, is going to be really important for highly functionalized materials. You can have functionally graded materials globally and have locally controlled properties using these mechanisms. It's also important that we identify new mechanisms in material manipulation. Finally, I think some promising new processes so far is lasers and surface evolution. All materials need to be post-processed. Using lasers could improve the not only the surface quality, machining, and you can control your at the same time. The control of thermal gradients. And also, one kind of caveat these hybrid processes is that they require an extra step. They have in situ processes where you have secondary process, the AM process, the secondary process. That adds to a lot of processing time. If we're able to scale up these hybrid laser utilization, that would be very finally, we sort of need a platform where all of this research is possible. Commercial machines aren't suited to hybrid processes, so looking at open concept machines is going to be pretty important. I've also included at the bottom that you can see that actually has a link to the data set that I've compiled from all of. So if you're interested, it is open and you can. So all the funding sources that have made this research possible, as well as all of my lab mates that have, I'd be happy to take any questions.
Awesome. Thank you so much, Samantha. That was a journey for sure. I learned so much. Great job. We have lots of questions, so we'll see what we can get to in the few minutes remaining. The top voted question is there a crossover between the hybrid process and regular AM with post-processing?
Can you say that?
Yeah, I think the answer is no. So maybe you can. Is there a crossover between the hybrid process and a regular AM with post-processing?
Yeah. So I think that's sort of the I was talking about, where I have considered a hybrid process with like you have your AM material, have a post-processing step. I think a lot of the times when people say hybrid AM, afterwards or machining it during. So that's where that's kind of contained. So there is like a mild crossover. We sort of had a rigorous definition of like, it's this plus an energy that it'll fit.
Gotcha. All right. Are these hybrid systems commercially available or only available within research?
Yeah, there are no as far as I'm aware, the current hybrid commercial systems are the machining ones that I've about. Using other energy sources or secondary lasers has not been implemented in where.
All right. Can you achieve higher resolution or smaller feature sizes with hybrid?
Definitely can. One was in refining grains, you can achieve smaller. I think that if you are clever with controlling your additional energy source, you could definitely get better resolution. And I also showed that you can get better surface finish as well.
Awesome. What is an example of a part using the hybrid AM process?
That's a good, there aren't many applications in this research. A lot of it is can accomplish making a material with these. Let me see if I have an example. I have an actual example, but I can't give a verbal example. Someone actually combined hybrid or combined metal AM and incremental forming, so that you could have a sheet that was going to be incrementally formed, and you would thicken the part needed it, so that you could do essentially have a rapid prototype of a sheet metal.
Gotcha. All right. Well, that is all the time we have for questions right now. Samantha, thank you so much for this presentation. And we're going to step down off the stage and get ready for the next talk. Thanks again.
So much.